Okay, thanks for the opportunity to give this presentation. Thank you very much for the invitation and the kind introduction. Just to clarify the European thing, ECMWF is independent. It's an independent organization. It doesn't depend on the EU, so no matter what happens to the EU, ECMWF should just stand as it is, hopefully. We, of course, have partnerships in the UK. We have projects that are funded by the European Union, including UK partners, so that's another story. But our formal constitution states the fact that we're independent. Our member states are nearly identical with those of the European Union, but not 100% identical. I would like to present to you a couple of things that relate to weather and climate. I saw that in yesterday's presentation there were already a few references being made to weather and climate applications. So this is something that we do 24/7 every day. I'm going to talk you through that. And then the title is quite long because it has high performance computing, it has big data, and it has AI in it, and it has European leadership in it. So I'd like to spend a bit of time on all of those, and this explains why the title is like an abstract, basically. So what it comes down to is kind of summarized in this graph, actually, because what we really want is we want to prepare information on the Earth system, so weather and climate, and that's current state, estimates, and forecasts for a very diverse range of users. There are some expert users, scientists like us, but there are also users in like the energy industry or reinsurances or everyday public like you, trying to plant your garden and prepare for the next dry and hot summer or something like this. So across that range, you have quite a wide variety of applications. And what we're trying to do is to prepare the information for it, okay? Based on the best possible description of the Earth system on physics principles. And what we need for it is extreme scale computing. I'm going to get to that. We produce a lot of data, and I really mean a lot of data. So this is probably one of the primary applications of big data handling technology. I'm going to talk to that. So actually, we're expecting in like 5 or 10 years dealing with exabytes per week. Right now, we do already petabytes per week. And then from that, you want to extract that information for all this range of users I mentioned. And ideally, what you want is that even the users can determine how this information is put together. So how the simulations work, how the observational data is used, and how then the specific information for specific application cases is extracted from that. So these are the three axes of technologies that we're talking about. Just a quick word. I was just asked why we're called medium range and what medium range actually means. When our member states founded us like 40 years ago, 45 years ago nearly, they wanted us to focus on the medium range because at that time, the medium range, which is like 3 days to a week to 2 weeks, was really terra incognita. So forecasts of important storms, for example, hitting Europe, like big Franz windstorms, like the famous windstorm in the United Kingdom in 1987 was not very well predicted at all. And the idea was to centralize financial resources, but also intellectual resources in a single place to change that. So to do something that no single member state can achieve on its own. Great idea. So we have today 34 member and cooperating states. The map is right here. Our member states own us. So they pay our budget. Our budget is roughly 80 million per year, half of which is spent on computing, half of which is spent on staff. So that's the rough idea. And what we do is we do our medium range forecasts. In fact, we do forecasts up to seasonal range, so 7 to 9 months. And all the data goes to our member states. We have commercial users as well. And then they do use these products and disseminate warnings, for example, when it comes to extreme weather, or if we sell our product to a company, then they do what they want with it. So we're less public-facing than a Met Service is. So if you see like warnings, they're being issued by the Met Office, for example, in this country, not by us. But we provide a lot of the information that's been used for that. So what we do 24/7 every day is we run a global prediction system. We create the initial conditions from observations plus a complex mathematical algorithm to put that together to describe the initial conditions, and then we run forecasts. There's different types of forecasts. The highest resolution forecast is 9 kilometers, so each grid box is like 10 kilometers, 9 kilometers big, and we run that out to 10 days. We also do ensemble prediction, that's what this is. An ensemble prediction is something that was actually founded in weather science, and it is based on the notion that neither your initial conditions or your prediction model are perfect. So what you want is not only a prediction of the atmospheric state, up to day 10, let's say, but also an uncertainty around it. Sometimes your 5-day or 10-day prediction is very accurate because you have very stable condition, so then your error bars should be very small. Sometimes when you have a regime change and the front is passing through, or you have very unstable conditions in summer, then your error bars will be large. But you want to quantify that size of the error bar based on scientific principles. So we run perturbed initial conditions and perturbed forecasts, and the perturbations are actually put together based on what we know about the uncertainty of the initial condition and the model itself. We do this with 51 members. So you get for each forecast a PDF of likely scenarios of weather. And you can imagine that this is costly because you run that at the same time and in the critical time path. So this is 51 times, this, except that it's at low resolution to keep it affordable. And we even run seasonal forecasts for something like El Nino, like mean changes of global state that we expect to happen on those timescales. When I mentioned European leadership in the title, so this is one aspect of European leadership. Since the foundation of ECMWF, it has been leading the global weather forecasting business. You can see this here. This is 3-day forecast. This is 6-day forecast of a certain metric, and you see these are errors of forecasts over a certain area. This is Northern Hemisphere, and you see that the red curve is below all the other curves. This is something that other countries actually are very jealous about, that Europe actually managed to put their resources together to achieve something like this. So we're better than the corresponding centers in the US and Japan and China. So this is really great achievement. Hard to maintain. Opportunities when this is in the press is usually hurricane season in the US. This is autumn, so like between June and November, when you have these big systems hitting the Caribbean or even the United States. And then our model tends to be in the press a lot, and these are just like little snippets we took from publications in the US. And this is the data, the underlying data. This is forecast error of track. So you want to know exactly where the tropical cyclone has landfall, for example. And that comes with an error. This error increases over time. So your 5-day forecast of landfall is worse than your 2-day forecast, for example. But you see that our model here, which is the orange, beats the others by quite a margin. So this is something that gives us a lot of publicity. Despite that skill, there are significant losses and impacts created by extremes, for example. This is based on a report that the United Nations published just about 6 months ago. And it collected all the numbers together about the impacts caused in terms of casualties, of fatalities, and economic losses by all natural extremes or natural hazards. And you see on the left-hand side is fatalities, on the right-hand side economic loss, and the numbers are actually staggering. So over that 20-year period, you have more than 1.3 million fatalities and more than, or close to $3 trillion loss by extremes. So despite all that skill, we're still very far away from what we really need as a society. Similar, the World Economic Forum in Davos meets on an annual basis. They write reports every year, global risk reports, and they issued this kind of graph where you have the likelihood of disasters and the impact, the worst being in the top right, so the most likely with the heaviest impact. And among those are really the ones that actually deal with weather and climate. If you look at extreme weather events, failure of climate change mitigation, natural disasters. So lots of the green things related to weather are actually in that top right corner. So there's really a lot of work to do. And a lot of it has to do with bringing together the skill that we have in the physical science, so to predict weather or climate, and what it does actually, so in terms of impacts. So if you think of what happened 2010 or last year, same story, you have, for example, a certain regime dominating European weather for a season, like the combination of a heat wave and a drought caused by a certain weather pattern. And then you can define a value chain or an impact chain, if you want, into many directions. For example, that causes vegetation stress, that's your garden, can cause forest fires, air pollution, affect human health. Or it causes crop failure with impacts on markets and prices and national economies, for example. So ideally, actually, we put together the modeling capabilities and data handling capabilities that we have already on the physical science side, together with the impacts straight away into one big prediction system, but we're quite far away from that. So that's one of the reasons why we cannot address these enormous impacts so far. Just two more examples on that. If you just think of how electric grids are managed on a daily basis, so this is weather, this is the wind, in fact, and then how that is projected onto injection rates of power into a grid over Europe and how that changes. So this is something that needs to be managed very quickly, very fast update rates in Europe, for example, for providers based on daily weather. But how is that going to change with climate? So how is it going to respond to extreme events that may hit one area or another? This is something we really need to get better at. Just another example which is relevant to all of us is this comes from a prediction of climate change impacts on temperature. And this is actually the wet bulb temperature, which relates to the fact, can you actually, as a human, sustain temperatures like this? Can your body evaporate enough moisture to cool down to the 36 degrees to keep you alive? And these predictions say that in areas where you find these blue-violet colors, you actually can't. So if you're outside, no matter how much you drink, you will die. So these are impacts that are important. So we need to understand how that works. Need to have the capability to predict that with sufficient reliability. Okay, coming to the science bit and the computing bit. We published a couple of years ago a paper on what are the future challenges in our area, exactly to address what I tried to tell you before. And there are like big areas in our modeling world where we need to focus. This was put together in a graph like this, where you have like resolution of problems. You have very small scale turbulence problems, even around buildings like this, for example, up to very large scale problems, interannual variability like El Nino. So these are global problems, these are local problems. And time scales are quite similar. So these operate on seconds and shorter, these operate on months and years. And what the model complexity actually is in order to represent that. This may be a very costly model, but you don't need much to actually do it. It's a Navier-Stokes problem. While if you go to a global problem where you need to cover atmosphere, ocean, sea ice, land, stratosphere, complex systems, your complexity goes up. And then in these rectangular areas, we highlighted the work areas we really need to focus on to improve our representation of all of that. And computing turns up to be the new big child, the new big problem area here. We always had trouble with computing, but of course Moore's law and stuff helped us exponentially over time, but it doesn't do any more. I'm going to come to that. But computing turns out to be really the major challenge for the next 5 or 10 years. And that has to do a lot with that we want to represent all that complexity and be and resolve everything at great detail. So let's talk about computing first. We actually said, okay, if we take that previous figure and we kind of think about what would a model, an Earth system model look like that we want to run in like 5 to 10 years. So what needs to be in it? What resolution does it have to have? So which processes do we want it to resolve? How fine the scales need to be? the complexity of it, how complex do we have to make ocean atmosphere, sea ice atmosphere composition, for example, and so forth. So we did a calculation on real computers with the models we have, and then we added factors by which this model that we could run would be inflated in terms of complexity and cost to project to what we want to run in 5 or 10 years. And this was published just at the beginning of this year. It's a paper that Thomas Schultes, the director of the Swiss Computing Center, key authored. So we did this with 2 models. One model that's run in Switzerland right now and ours. And the table puts together these factors, but the important ones are the factors at the bottom. So our shortfall, so current model projected into the future, needing to run at a certain pace as well. What's the shortfall of today's capabilities? And the order is like between 60 to 50. So let's say order of 100 or 200. Okay, so we're right now about 100 times too slow with our systems, if we keep them like this. Now, our systems do not include atmospheric composition really, so you have to add a factor for this. We kind of know that factor because we run very poor systems of that, but the factor is kind of known, so you would have to add to that a factor of 3 to 5 for that. And then I mentioned earlier, we want to run ensembles to characterize the uncertainties. You add another factor of 50 or so for that. So in the end, you're at least an order 1,000 short. That's really a problem. I mean, we've done this for many decades. We're really good at computing, I think. We're still based Fortran. So we heard that yesterday, the unhealthy mix of Fortran 7790 and whatever we think it is. But it's improving. I'm gonna come to that. But it's highly tuned. It's OpenMP, MPI. So we use everything that's kind of there, and still we're a factor of 1,000 short. This is how this plays out at ECMWF. So we have, I mentioned, half of our budget goes into supercomputing. So we have a big computer hall where we have like 2 clusters of 4 petaflop each. That's peak performance. But this shows kind of the timeline over the years of the different supercomputers we had and the sustained performance. And then that allowed us to kind of, for example, crank up the resolution in our model and run more complex systems, have more data and so forth. So right now, for example, we're running, I showed that on an earlier graph, a 9-kilometer model that's 6.5 million grid points, 137 levels, 10 prognostic variables, about 2,000 time steps to be calculated within an hour. Okay, that's a serious problem. So this is the past. I mentioned the factor of 1,000. If we just go back, a factor of 1,000 was achieved in like 15 years just by chips getting denser and so forth, and clock speeds going up, same energy density. You know the story. So that's not going to continue in the future. So we can't just bank on this line going up. Known story. The other problem we have is actually that the ratio between sustained and peak performance decreased over time on our machines. So we started with crays, little cupboards, to our big computer hall today, where we reach about 4% sustained performance. So it's not only the problem with Moore's law and stuff, it's also that our codes become less efficient on supercomputers. So let's have a look why that is. This is taken from a paper that Brian Lawrence, NCAS director in Reading, wrote a year ago about. And it shows in these task graphs of what's actually happening in the model. So we dig now into the model and see where these inefficiencies come from. So, and they look very similar if you look at our model compared to one that's run in the US. GFDL sits in Princeton. The Met Office unified model. So kind of the same, because in the end, you're dealing with the same type of physics. You're dealing with Navier-Stokes equations that you solve in a discretized way over the globe. And then you add your individual physics processes like radiation, clouds, convection, all that, surface. And then you cycle through your time-stepping scheme. So you'd say, like, based on that, it's not very obvious that there's a fundamental problem in the layout of our model. But we have experience with this because, flow diagrams like that always look simple when you just look at them. But then when you do a reality check, and this is a reality check for an ocean model, you see that what actually happens in the execution over time, your graph that looked so simple before becomes really, really complex. And an ocean model is fairly simple, actually, compared to an atmospheric model. So it's really, that's one of the issues. You know, there's lots of dependencies, there's cyclic dependencies. Many things are just costly because they're called a lot. Because, you know, 6.5 million grid points, you call a lot of processes every time step and so forth. You have subtype stepping for certain processes. So it's really, really complex. So let's dig into this a little further. So this is a different rendering of what I showed before. So it's a succession of individual processes that are taken care of in our equations every time step. So every time step you go through this once. So you start with something where your dynamics, so your Navier-Stokes equations are calculated and iterated, let's say. And then in our case, we have a global spectral model. So that has very nice features, but it also has problems. More to that later. More about that later. So we do a spectral transform from wave space to grid point space every time step and then back at the end of the time step. So that adds calculations. It also involves global communication. So that's an issue, and it's a very specific issue. It's something that hits us twice per time step. We advex stuff, so this is moving stuff around. You know, if you heard, for example, yesterday the application example of Fukushima, I think it was in your talk, no? Where you advect your pollutants in the atmosphere, and you look at transport, how that is transported over time from A to B. That happens with advection. You do that, of course, for composition, but you also move clouds and water vapor around. So everything that's in the atmosphere is advected in some way. That's a different problem. It has halo communication because you need to know from where you move into a different location. It doesn't scale very well. We have physics calculations. So these are the grid point calculations, radiation clouds and stuff. They're expensive in part, and you call them just a lot. They're scalable though, because they're single column calculations. Then you couple that with an ocean model or waves. These are expensive in themselves. They have complex solvers as well, just like here. Then you couple at the interface, and then the solver of the whole complex system, and then you transform back. So if you look at what I wrote here, not the bold ones, but all these things, they're quite different. So twice per time step or once per time step, you do very, very complex and very different things. And if you put that together, even if you optimize one component, you still have a very inefficient system. That explains why our sustained performance is so poor. Just to show you here a profile of activity taken with the tools that Barcelona Supercomputing Center is offering. So here you have different processes in the atmosphere and in the ocean. And while you do calculations in the atmosphere, then you couple, and your ocean does calculations, your atmosphere is waiting for that, you know? So this is something where you have a give and take, a handshake between the two. So that's very difficult to parallelize, just for example. So we have quite a good idea of why that is inefficient. So we did a lot of work, and I can't go through this in detail, on optimizing the individual components, you know, trying different programming models with the existing code, upgrading our Fortran to something else, using different programming models to exploit the existing parallelism, overlapping more communication and computation. So the usual stuff that everybody's dealing with, we've done that, okay? And it doesn't give us the factor of 1,000. It gives us maybe a factor of 2 at best. So the conclusion from everything we've done over the past years is really that we have to touch everything. So in the end, that factor of 100 or 1,000 can only come if we really rewrite our codes. And our code, just our code, is about 3 million lines of Fortran, C++. And we have around that, to run that stuff, about 200, 300,000 lines of scripts to just, you know, deal with everything else, tasks, data, input, output stuff. So in the end, we need to change that. And that graph is based on the idea that we need a lot more flexibility at the top end. So in terms of algorithms even, which we thought in the past, kind of we know what we're talking about. We know how to solve our Navier-Stokes equations. We started to think maybe there's better ways of expressing things. And maybe sometimes you don't need to be that accurate, but you can be a lot cheaper and invest that gained efficiency into some other area. So we need to question actually the way we address our science problem to start with. And then at the bottom is probably the area that's dealt with a lot here. how do you actually map this onto memories, onto parallelism that different types of architectures offer? So this is kind of the thing, the separation of concern idea. And in the middle, we believe actually that domain-specific languages will be the solution one way or another. So how they look and how general we can make them for our problem needs to be seen, but we have started. So at the bottom, we need, at the top, we need algorithmic flexibility. And that can mean, is our spectral global model a good approach? Should we use a grid point model? But time stepping is really costly. So some infrastructure that allows us to try out different types of algorithms, and maybe some are less accurate, still stable, but map better onto architectures that are on offer. Maybe artificial intelligence, I'm going to come back later to that, offers some efficiency gains. And at the bottom, we need libraries that allow us to define backends that are hardware specific. And ideally, the scientist that works with the stuff on top doesn't see that. So that's the separation where you really have some sort of simple code, MATLAB or Python-like code at the top, and all the hardware dependence, all the parallelism that you want to expose, vector technology as well, of course. So everything that somehow maps onto optimization and hardware is at the bottom and hidden away from that. So the scientist who is not a computational scientist can't break it, but can still do science. So that's the idea. But for something like that, of course, with an operational system where you update your code anyway, scientifically every day, it's quite difficult because you're basically changing your wheels while you're driving. So that's something that we're trying to approach in individual projects right now. So one of the projects where we're doing this is called ESCAPE. It's funded by the European Commission. It ran between 2015-18. Now we're in the second phase of it, 2018 to 21. And it goes back to this fundamental idea of this, where you say, I have through my time-stepping individual components, they have very different computational bottlenecks. So why don't I take that apart? So I isolate these individual components. We call them dwarfs. They are functional units, so they have a specific meaning in what we do every time step. For example, a dwarf could be this advection scheme. That's a functional unit, and it comes with very specific computational patterns. Then we try to adapt that to suitable processor types, whatever is around, test optimized performance. You do that for everything, and then you put it all together again. Example, I mentioned before the spectral transforms. So this is a very costly part. Spectral transforms, in our case, global model. So fluid on the sphere means that in latitude direction, you do FFTs, and in longitude directions, you do Legendre transforms. The FFTs are quite quick compared to the Legendre transforms, and the whole package together is fairly slow and involves global communication. So if you run a problem like that, so that's a dwarf, you can run that in isolation. You can crank the size of the problem up by adding more wave numbers, which is basically equivalent to resolution. So this is a fairly small problem. 159 would be a global model resolution of about 125 kilometers. So it's fairly small, the problem. So you can run it on a single GPU, for example. And here, roofline plot, I'm sure most of you have seen it. Blue line indicating that this sloped part is limited by memory bandwidth, and the flat line up there by clock speed. And you want to go right because you want to have more operations than you move data, and then that allows you to exploit the top right corner there. So what we achieved in this project, for example, by optimizing this particular problem for a GPU, is a performance increase by roughly a factor of 25. So that's something that for specific problems you can actually achieve. So you really throw everything at it that this type of architecture offers you. So that's a fairly good result. When you do that for bigger problems that don't fit on a single GPU anymore, and you run this across multiple GPUs, then you have a communication bottleneck potentially. In that project, we used a new technology that NVIDIA is offering, which is NVSwitch, which is a very fast interconnect between a limited number of GPUs. And we actually achieved another factor 2.5 just by doing that. So GPUs without that fast interconnect, with that fast interconnect, factor of 2.5 is doing the same thing. So, 25 by 2.5 is a factor of 50. So this is something what we achieve right now for individual components, just for GPUs, and we're trying other things. So that's a good story. Within another project called EUREXA, we're doing something similar. This time we're looking at FPGAs, for example. They have been mentioned yesterday as well. In this particular case, we take a different problem. It's a cloud scheme, so a different dwarf. Different computational pattern. But we basically apply a similar type tool chain that we want to build in when we talk about domain-specific languages. We have some sort of a generalized intermediate representation, translation into then hardware-specific code types, which could be different as you go along. But if you have that variety here or these different options here, you would not necessarily. This code would not look any different. So this goes ideally through auto translation options. We've heard examples yesterday. And this is what we do in this project. And what we achieved in a simulator, because we're right now working on the actual hardware itself, in the simulator we achieved about a factor of 4 improvement for an FPGA. That's in terms of speed. And as you showed, I think yesterday, in terms of energy efficiency, that's probably better than that, So this is a consideration. But we're working on these aspects for these limited size problems. We're also scaling that up. We actually have applied for a project to run our problem on the biggest computer in the world, which is the Summit machine in the US in Oak Ridge. Right now, bottom right there is the specs. That's an IBM Power 9 plus GPUs. So we have a 1-year project running our entire model at a very high resolution. So this is kind of the resolution that we think we kind of need globally to really make a big step in the future, and to scale that onto this machine. And we're trying different algorithmic options. That was the top end of that touch everything graph I've showed you before. So we tried different kinds of numerical approaches head-to-head on that machine, and how that scales at that resolution across the entire machine. Something we just started. A result here with the current model. That's a strong scaling example. We get the green curve. So this is nodes on Summit versus nodes on Pitt-Stein, which is the biggest machine in Europe. So this is a Cray. Has Broadwell's plus GPUs. This has the Power 9 plus GPUs, different generations of GPUs as well. But these are just CPU calculations. And that is the throughput we achieve. And throughput for us is important. I mentioned earlier, we're running 6.5 millim grid points, blah, blah, blah. And we need to complete that calculation in an hour, because our users, member states, are waiting for a forecast. It's scheduled every day, so that needs to be ready. So that's a hard margin or a hard limit for us. So that translates in our case to 365 days per day. So this is a factor of 3 short, but then this is just the atmospheric model. It doesn't contain all the complexity that we require. So the factor of 3 comes back to a factor of 100 or 1,000 if you do the real calculation, okay? But you see already that machine outperforms what we have in Europe. And then next step is to do that with GPUs. But we did already our spectral transform problem on the Summit GPUs as well. So this is not the entire model like there, but just for the spectral transforms, which are about, in terms of cost, 1/3 of the total cost of the model. So it's quite representative, actually. So this is the number of MPI tasks across GPUs and how that scales. This is on the CPUs, this is on the GPUs, and that's a log scale, so that's a significant factor, actually, that we achieve for this particular problem with the version that we produced in ESCAPE. So to leave you with the conclusion here for the computing bit, we have a very complex system. It's composed of a multitude of sub-problems that are very different. Right now, we're trying to break that up, manage individual tests on individual hardwares, but in the end, what we need to do is to generalize the whole thing, build the middle part, which is the domain-specific language bit, which we're about to do, and to then put it together so that we can run the entire system on any heterogeneous architecture that's out there and that's coming. So big data, that's the important axis in the middle, because in the end, the modeling part is important, but what we really want is the information, and that relates to data. So our data flow looks like this. We acquire a lot of observations per day because every forecast that we do needs to be initialized. So the starting conditions for the forecast need to be established as quickly as the forecast actually needs to be run. So per day, we collect observations of the order of 40 to 60 million, mostly from satellite data, but also from balloons and all the stations that are out there. So this is in itself quite a logistic effort, actually, because the data needs to be with us quick. So between recording and usage at our place, usually you spend 3 hours. So a certain measurement being made at a satellite, for example, being transmitted to a ground station, pre-processed, received by us, and then digested or ingested, 3 hours. So that's quite a tough problem. So 40 to 60 million every day. We then create our initial conditions, the forecast model, and then we do generate products. So you take your model output and then create all the products that our member states and users want. You dump everything, you archive, you save everything that we ever produced. We have the biggest meteorological archive in the world. There's lots of simple to access products for the web service where people just look. And then a lot of the raw products and intermediate products are actually disseminated via a specific network, fast, high-speed network to our member states. So there's like 3 levels of data processing. It's quite a complex workflow. So if you look at just the operational profile of that at ECMWF in terms of compute nodes accessed and then data being produced. So our schedule, because we do this at prescribed times every day, you get a certain allocation of compute nodes for the individual components of our forecasting system. I mentioned the ensemble, the initial conditions, the forecast, and all that. So this is always at the same time. This is 12 hours, so times 2. We do this twice a day. So you see that one of our machines is at certain times of the day fully allocated to that stuff. But don't forget, we have 2 clusters. We do a lot of research. Only 25% of our computing capacity is actually allocated to operations. The other 75 is research and member state allocations. So our system is actually 4 times as big as this altogether in terms of capacity. So, but just going back to the operational, that's why it's underlined here. So that compute profile translates to this in terms of files touched. And this is 10,000, this is 100,000, this is 700,000. So you see how many files we're actually dealing with at very high, very fast rates. And then this is data rates in gigabyte per second, and this is 0 and this is 25. So we have a very important traffic during the day in terms of files being accessed and data being transmitted from A to B. All right? So in total, we have a total traffic just from operations per day of about 650 terabytes. Some is pulled, some is pushed, 650. About 1.5 million requests that we need to deal with. And our total archive right now is 220 petabytes. So per week, right now, we're dealing with 1.5 petabyte. And I mentioned earlier, we're thinking exabytes in 5 to 10 years. So that's a serious data problem, but it's also a serious workflow handling problem. If you're dealing with 1.5 million requests per day, how do you manage that in a workflow with a file system, for example? So right now what we do is, looks like this. This is in red, the time critical path, 1 hour window. So this happens all in 1 hour window, in a 1 hour window. I mentioned the timeliness requirements. So we run our model. All the data goes onto disk. We pick it up from disk for our product generation. We dump that again on disk, and then it's being disseminated. And this is time critical, and then eventually this is going to end up in our archive. And of course, as you can guess, doing this and doing that, this is not very efficient. First, you go to disk, and secondly, you do it multiple times within an hour. It's not very effective. So what we are aiming for, and part of this we actually have already realized, is that we don't touch disk in that 1 hour. No? We do calculate the forecasts. We deal with a different type of database in the middle that doesn't need disk. And in the end, everything is happening like kind of in memory and on the fly, being streamed to the recipients. And only eventually, outside the time-critical path, that data ever sees the disk or the tape archive. So we have actually most of that already implemented. So ingredient number 1 to this is that you deal with data in a different way, that you do not use files that you read and write, but you use something in the center that's what we call object data store. I think that's a common term, where you deal with data in a much more flexible way and it's not files-based. So that exists already. FDB, this is what we call fields database, is based on a certain language that we've been using for some time already. The values are byte streams. It's not organized in files, as I mentioned. And that is going in actually already this year. Totally different way of dealing with data away from files. And the other thing is, the other advantage of that is that this can in theory deal with any kind of backend. So whatever technology you have underneath of where you store your data or through which means you stream your data, it doesn't matter if you deal with that. So that's a very important ingredient to that. Ingredient number 2, deeper memory hierarchy. This is something where a project that was managed here, EPCC, helped a lot, called NextGen IO, which looked at the potential of what's called 3D X-point NVRAM technology offered by Intel, assembled by Fujitsu. Actually helped to close what's usually called this memory gap, where you have the hierarchy in terms of data rates, access rates, and bandwidth, that one by something new. This technology is coming and actually allows to manage with very large volumes of data at very high rates before it sees disks, for example. And so you can use that either as a memory extension to actually do calculations, or you outsource specific tasks that you want to have run in close link, like a on-the-fly calculations alongside your model calculations. So perfect for our problem, because we run our model, let's say here, and then our product generation, which needed to go through the disks before, is just run alongside the model in this space without needing that. Okay, so this is where that project helped a lot. And actually, when we compare the current allocation we use for doing this on our usual Cray nodes, 288 Cray nodes for doing product generation, gives us that kind of data rate. And the new technology explored in the NextGen IO project gives us a fairly similar data rate with only 34 nodes, but with that 3D X-point technology. So really great potential for us and very easy to manage. But still, in terms of overall archive, so in the end, everything goes to the archive, we have a problem. Today, we have 200 petabytes. Again, that curve of computing. But on the right-hand side, you have the corresponding archive size. So as you have an exponential growth of computing power in our system, your archive grows exponentially as well. And we cannot afford to multiply 200 petabytes by 1,000 in 5 or 10 years. So it really requires a totally different approach. That's something we have to deal with. But I'm proud to say that regarding the object-based store, the object-based data store, and like what we have available with technology like NVRAM, we're already very far into what we can do in operations. Actually, much further advanced, I think, than with the previous example on domain-specific languages, because that is such a complex problem. So let's talk, after proper intelligence, about artificial intelligence. There is a potential for that in our sphere. If you're actually interested, you could just read one paper, which is quite nice, that was published recently in Nature by Markus Reichstein, on deep learning, process understanding, and Earth system science. And it basically looks at, you have the problems that we're dealing with 24/7 in our place and other places. So you have a lot of information there, and you're trying to extract knowledge, so to turn data into information is what that means. But at the same time, on the right-hand side, so the way this data is being used, usage patterns and different types of information can also help you drive that data, how you generate and do that data, deal with that data. And the example they have also in the same paper is here. On the left-hand side, like the classic machine learning applications for image analysis, for example, where you do object classification, recognize this is a dog, or where you do resolution enhancement, for example, with statistical techniques, or even prediction, video prediction, you know, like a first guess of what the next picture looks like, or language translation. So the analogies for Earth system science are here as well. Pattern classification, you know, you want to recognize tropical cyclone statistics from you know, petabytes of data that we produce. You can do downscaling to try to enhance the resolution over a certain region to give you more specific information, spatially prediction as well, for example. So there's lots of analogies. So this is a nice overview paper. And what that translates to is basically this. I've shown you the workflow before. So data acquisition, you know, initial conditions, forecast, product generation, and then data assimilation. There's basically three big application areas for us where these kind of technologies can help. One is on the data acquisition and dealing with observational data side, which is, I mentioned 40 to 60 million observations per day. In the future, you may have IoT devices that add to that. You know, everybody's mobile phone can take pressure measurements, temperature measurements, but you want to know if the person is inside a building or outside, or if the phone is on the coffee table in the sun or not, you know, these kind of things. So how to deal with the quality of data, how you manage data quality and eventually select the data that you want to use, for example. But also to combine information from different observations spatially or different observation types. And then in the prediction model side, I mentioned that in my touch everything graph, certain components of our forecasting system, and I'm going to come to that in a minute, are very expensive, and there may be a potential to replace them actually in operations just to save time with deep learning methods, for example. So and then on the output side, I mentioned petabytes. You know, how do you extract information? So this diagonal axis in the slide at the front of the presentation. So how do you create information from data? From how you go from exabytes to the actual kilobytes that a specific user wants. So there's a lot to do on data analytics. So the first thing we looked at was, okay, all this is probably true, but can we actually predict the weather itself? So why bother with 3 million lines of code? You know, why not just train a neural network with past forecasts, let's say, or reanalysis data sets over decades, and just save your breath and do the whole thing. So we did that. We wrote a paper about that in a simplified way, but what it basically turns out is that you have a very big problem that's very nonlinear. Number one, it's a chaotic system, and you have billions of degrees of freedom. And that's very difficult to encapsulate in a deep learning method, unless you make the deep learning method as complex as your physics model. So in the end, you may not save much. I'll show you an example of that in a minute. But what we did in that paper is we took a very coarse resolution problem. So this is really like 2.5 degrees, so 250 kilometer prediction. And we trained the neural network to predict the weather or a certain parameter at one point, knowing the surrounding points from a training data set, and then you predict the one. And this is what you get. You know, this is the error of the network over time. So this is forecast time. This is an error. So this is the error of the network. This is the error of the real model in this very low dimensional problem. But in the end, you know, with our operational system, we kind of sit here. And there's like 6, 7, 8 orders of magnitude of complexity between those. All right, so not trivial at all. But I mentioned earlier, why not look at individual components? I mentioned to you the spectral transforms, which are really, really expensive, but they are very hard to replace with methods like this. But our model physics, radiation, waves, clouds and stuff are very expensive as well. So that's a third. That's, for example, a reason why we run our radiation scheme only over a coarser grid and not every time step, just because of cost reasons. So we started a collaboration with NVIDIA to actually look at radiation. So we take the radiation problem again as a dwarf. We use all the input parameters the radiation scheme needs, so like profiles of temperature, moisture, and stuff, and clouds and stuff, and predict what the radiation scheme produces, which is like radiative fluxes through the atmosphere that causes then heating by radiation or cooling by radiation. So we treat the radiation problem as a black box. And what we achieve in terms of calculations is something like this. So this is South America. So this is the Atlantic here. So this is where you have daylight. That's shortwave radiation. So you only have that where there's daylight. This is night. That's the real radiation scheme. That's the neural network, which looks at first glance not too bad. But you have locally quite large areas. These are classified here. This is vertical. This is different types of fluxes. So these areas where the areas are large are usually the parts where you have clouds and lots of nonlinear things going on. So it isn't perfect, but it's a first good start. But coming back to the numbers, you can define different types of network designs, architectures, deeper, wider, to do your problem more accurately or less accurately. And if you look at the radiation scheme, that takes a certain time. And the opposite ends of neural network designs, one very fast but simple, and one less fast but more accurate, that one is almost as costly as this. So you really have to have a very close look at the trade-off between accuracy and speed for that. But there's potential, and this is why we're doing this. And we think the radiation scheme could be a candidate within the next couple of years, actually. So, last point, European leadership. I mentioned already the leadership in terms of where we are, in terms of predictive skill today, and that Europe has made a specific effort, creating our center, for example, but altogether being very good at this. The Met Office, for example, has a very good prediction system that's nearly as good, and certainly better than the Americans, the Japanese and Chinese. So there's really, in Europe, you have to say, an epicenter of skill for this kind of problem. That's very good. And because we face the challenges I mentioned about computing, about data, about actually understanding the processes also better, it's not that we know everything that there's to do, and it's just a matter of engineering it onto big computers. We have invested in a large variety of projects and efforts in multiple axes. And one of the axes is the science of prediction, where we actually try to improve our science. It has nothing to do with computing in the first place. It's really about better understanding of processes at high resolutions, how you couple oceans with atmospheres, what are the important processes to encapsulate. So there's a whole range of projects funded by the European Commission, actually, of doing that. But there's national programs as well. I just put here what's available under Horizon 2020. So there's a lot going on, and we're quite well organized in terms of improving our science of the prediction. And then that is complemented by the projects I spoke mostly about, which are about, if you have that science, these are your science ambitions, how you bring this on computers efficiently so that actually, if you want to run a global model at 1 kilometer with lots of creating petabytes per day, how do you actually manage that? And this is what all these other projects are about. And then we have another level, which is actually fora where we do not just do that for a specific model and a specific problem, but where we propagate what we learn from all these projects up here and have the entire community benefit from it. So it's actually a quite good mix of these things. But as you know about these projects, they are 3 years, you get one, you don't get one. You can't always determine what they're about, so it's very patchworky. So the real question, and this is the one I want to finish with, is, given that we have established this, and I think this is successful, and it's a story about European leadership actually, because we managed to do all that, and it creates a great basis for collaboration. But how do you adjust that now and make it sustainable, given national and European and international programs that provide the money? And Euro HPC is another presentation on its own, I guess. So the real question is, European leadership, yes, but can we actually sustain it? And can we actually achieve what we need to achieve to address one of the biggest societal challenges of our generation? And I mentioned these very big impact and risk factors that we have from weather extremes and climate extremes, that despite our knowledge and our predictive skill are still unaddressed. So if we need to deal with this in the next 5 to 10 years, You saw the demonstration yesterday in Edinburgh downtown about the climate challenge. You know, this is something we have to deal with in 5 to 10 years. So is that really sufficient to deal with that? And I don't think it is. And the solution next time. But with this, I would like to thank you and finish with a nice little animation while we do questions that's been produced by Hamburg. That is very high resolution, but unfortunately a factor of 100 or 1,000 too slow. Thank you.